Welcome to The Explainer. Hook yourself in and boot up your visual interfaces because today we are stepping into a dark, holographic lab simulator. We are going to trace the absolutely incredible physics of geometric optics. We'll be manipulating glowing neon rays of light to figure out exactly how images are formed, bent, and projected through the fundamental laws of reflection and refraction. Let's dive right in. Have you ever been lost in a mirror maze? It's a completely wild experience, right? But the crazy thing is, a mirror maze uses just simple, perfectly flat reflecting surfaces, yet it completely manipulates our perception into seeing a seemingly endless hallway. By merely redirecting light rays that emerge from a source, these flat mirrors create composite images that completely trick the human eye. We are going to decode exactly how this illusion actually works. Here is our flight plan for today. 1. Images and plane mirrors. 2. Bending light with spherical mirrors. 3. Refracting at spherical surfaces. 4. Focusing with thin lenses. And 5. Engineering optical instruments. All right, kicking things off with Section 1, Images and Plane Mirrors, the flat foundation. Okay, before we start playing with our neon rays, we have to define the absolute cornerstone of this whole explainer. What exactly is an image? Well, an image is simply a reproduction of an object via light. Now, if the light rays actually physically intersect and can form on a surface, think of a movie projector hitting a screen, that is a real image. It's literally there, even if nobody is in the room to see it. But if the image requires an observer's visual system to exist, meaning your brain is basically doing the heavy lifting, extending those diverging light rays backward to a point where they only seem to originate, like when you look at your own reflection in a bathroom mirror, well, that is a virtual image. And this brings us to our very first fundamental rule. When you're dealing with a plane mirror, which is just a perfectly flat reflecting surface, the apparent image distance, which we call I, is always the exact negative of the physical object distance, or P. The light rays hit the flat mirror and bounce off, but your brain traces them backward. So if you're standing exactly 2 meters in front of a mirror, your virtual image appears exactly 2 meters behind it. Simple as that. Moving right along to Section 2, Bending Light with Spherical Mirrors. So what happens when we curve that mirror? Well, it completely changes the game. It totally alters how it bends the light path. First up, we have the concave mirror. It curves inward, kind of like walking into a cave. It has a positive focal length, meaning it focuses our neon rays together to a real physical point in space. Because of this, it can actually form both real and virtual images. In sharp contrast to that, we have the convex mirror. It curves outward, scattering the light rays away. It has a negative focal length, and because of that spreading effect, it can only ever form virtual images. This scattering also impacts the lateral magnification, meaning convex mirrors produce smaller, demagnified virtual images. That's exactly why you see them used as wide-angle security mirrors. Now, the absolutely crucial thing to grasp here is how the physical position of the object completely changes what you see. Take the concave mirror, for example. If you place an object inside the focal point, so really close to the mirror, the image is virtual and right side up. But pull that object outside the focal point, and suddenly the image is formed on the exact same side as the object. It becomes a real image, and it literally flips upside down. You don't always need complex math to figure out where an image is going to be. You can actually just map it out visually through something called ray tracing. It's like a geometric puzzle. Step 1, you just draw a ray parallel to the central axis, which then reflects perfectly through the focal point. Step 2, draw a second ray through that focal point, which reflects back parallel to the axis. And step 3, draw a ray through the center of curvature, which just bounces straight back on itself. Boom! Where those 3 glowing rays intersect on your readout, that is exactly where your image forms. All right, let's shift gears to Section 3, Refracting at Spherical Surfaces. To really wrap our heads around refraction, picture this: a Jurassic mosquito perfectly entombed in a piece of ancient amber that has an index of refraction of 1.6. The outer surface of the amber is spherically convex. Now, when a scientist looks directly at the mosquito through this curved surface, it appears to be buried about 5 millimeters deep. But how deep is it really? Because that convex refracting surface actually bends the light rays as they exit the amber, the image is visually displaced. The true object distance is actually completely different from the image distance we perceive. Now, here is a massive gotcha that trips people up all the time. When light passes through a refracting medium, the rules of geometry literally flip compared to mirrors. Think about it. For a mirror, real images form on the same side as the object,
because the light bounces back at you. But in refraction, the light travels right through. Therefore, real images form on the side opposite the object, while virtual images form on the exact same side as the object. Definitely keep that locked in your memory banks.
Which brings us nicely to Section 4, focusing with thin lenses. Get this, you don't actually need highly engineered glass to manipulate light. Any transparent medium with a different index of refraction from the air around it can bend light rays. You could literally use a chunk of frozen ice shaped into a convex form. It's incredible. This perfectly demonstrates the whole concept behind the lens maker's equation. As long as a medium has a different index of refraction than the surrounding air and uniquely curved surfaces, it is going to bend and focus that light. Just like our curved mirrors earlier, thin lenses basically come in two distinct flavors. First, converging lenses. These are thicker in the middle. They have a positive focal length, and they elegantly bring our parallel neon rays down to a sharp, pinpoint real focus. On the flip side, we have diverging lenses. These are thinner in the middle, they carry a negative focal length, and they take those parallel rays and spread them wide apart, so they seemingly originate from a virtual focus behind the lens.
All of these variables are governed by the thin lens equation, but we can organize the outcomes pretty simply. Notice the beautiful symmetry here with our earlier mirror math. A converging lens acts a whole lot like a concave mirror. Put the object outside the focal point, you get a real upside-down image on the other side. Put the object inside the focal point, you get a magnified right-side-up virtual image on the same side. And the diverging lens, well, it's the steadfast equivalent of the convex mirror, only ever producing a smaller virtual image.
And finally, Section 5, engineering optical instruments. So what happens when we start combining these thin lenses? We literally unlock the macroscopic and macroscopic universe. It's a rapid-fire upgrade sequence. First, the simple magnifying lens uses just a single converging lens to increase angular magnification, making objects appear way larger on our retina. Step it up, and we stack two lenses to create the compound microscope. An objective lens creates a real, enlarged image of a tiny object, which then acts as the new object for an eyepiece lens that magnifies it even further into a virtual image for our eye. Finally, the refracting telescope completely flips the script. It uses a massive objective lens to capture parallel light from distant galaxies. Focusing it down before an eyepiece magnifies that cosmic light for the human eye. And that brings our simulator run to a close today. But just think about this for a second. By understanding something as simple as whether an image is real or virtual, and mastering just a few basic equations governing the bending of light, humanity built the actual tools to discover bacteria, human cells, distant planets, and neighboring galaxies. We quite literally changed human history forever just by curving glass. So, as you leave the lab today, ask yourself, what invisible worlds will these fundamental laws of geometric optics reveal to us next? Thanks so much for joining me on this explainer, and keep looking closely at the world around you.